Okay, so if you should on your own verify that ux squared plus uy squared is equal to c squared. It better, because right, the speed of light should be the same in all reference frames. Um, but let's move on. So let's calculate the angle theta, which is measured by in the reference frame, in the unprimed reference frame, the one that's not moving with respect, the one that's um, let's say stationary, and the source is the one that we're considering to be moving. Okay, so if we look at the primed frame, we notice that cosine theta prime is just ux prime divided by c, and we've written it here basically. Ux prime divided by c is equal to cosine theta prime. So similarly, ux divided by c is equal to cosine theta. That's the angle measured in the unprimed frame. Okay, and this is just equal to cosine theta prime plus beta divided by 1 plus beta cosine theta prime, where basically I've divided the top and bottom by c. I've divided this equation for u of x, the top and bottom, by c. Well, it's divided by c, and so that gives you this expression. Okay, so for theta prime is equal to pi over 2. Okay, so for an angle, for an array which in the source's frame is emitted transverse to the direction of motion, then cosine theta prime is equal to 0, and cosine theta is equal to beta, right? So if cosine theta prime is equal to 0, then cosine theta is equal to beta. Okay, and so as beta tends to 1, that is, as the velocity, the relative velocity between the two frames gets close to the speed of light, then the light is concentrated in the forward direction. Why? Because if beta gets bigger, that means the cosine of theta is getting if beta gets larger, that means cosine theta gets larger, and that means that theta is getting closer to 0. Okay, and so this is the headlight effect. Basically, the faster that a source, an isotropic source, a source which is emitting in all directions, the faster it moves, the more the light from an observer's point of view, who's at rest, let's say, with respect to this moving source, then the light gets more and more concentrated in the forward direction. Okay, so that's the headlight effect. Okay, the final effect we're going to consider is superluminal motion, or apparent superluminal motion. Just to set this up, this is an actual real, based on some real observations. Quasar 3C273, which is a real named quasar, there's motions with angular speeds of 0.8 milli-arc seconds per year have been observed. Okay, and this quasar is located about 2.6 times 10 to the 9th light years away from Earth. And so the question is, let's first calculate what the apparent speed of this quasar is, and let's leave this in terms of light year per year. Our intuition is that you should never get any motions bigger than 1 light year per year, because 1 light year is the speed that is the distance that light travels in 1 year, and so you shouldn't get any speeds bigger than that. But let's see what we get. Okay, the first thing to realize is that a milli-arc second, 10 to the minus 3 arc seconds, there are 3,600 arc seconds in a degree, and pi radians per 180 degrees. So if you do the math, dimensional analysis, you get that this equates to 3.9 times 10 to the minus 9 radians per year of degree shift.